Good morning, everyone. I am Tarun Kumar from Global Academy of Technology. Today, I am excited to present my project titled AI Driven Air Quality Index Prediction using Machine Learning and Deep Learning. The problem and motivation of our project is air pollution is currently one of the most critical environmental threats we face. According to the World Health Organization, it is responsible for approximately 7 million premature deaths each year on a global scale. Urban areas, in particular, often exceed safe pollution thresholds, posing serious health risks, especially to those with respiratory or cardiovascular conditions. While many existing tools provide real time air quality data, what's noticeably lacking is accurate prediction of future air quality. Our motivation for this project was to address that gap. We aim to create a system that not only informs users about current pollution levels but also predicts future air quality. This empowers both individuals and institutions to make informed, health conscious decisions in advance. Project objective. Our objective was clear to develop a system that can accurately predict the air quality index while ensuring it is both user friendly and suitable for real world deployment. To achieve this, we designed a hybrid model that leverages the strengths of two machine learning algorithms, random forest and gradient boosting, along with a powerful deep learning model, LSTM. To enhance usability, we implemented a graphical user interface using tkinter, making the system accessible to both technical and non-technical users. The key features of our project are that we have achieved an R squared score of over 0.99, which indicates that our predictions are extremely close to the actual values, demonstrating the high accuracy of our system. To make the tool accessible to everyone, we have developed an interactive graphical user interface using tkinter. This interface allows even non-programmers to upload air quality data, pre-process it, and train models with ease. Our system supports real-time training and monitoring of the air quality index, enabling users to see the model's performance as it learns. We have implemented an ensemble approach that combines machine learning and deep learning models, including random forest, gradient boosting, and LSTM to enhance prediction reliability and performance. The training process is fully transparent, providing live feedback during model training so users can better understand the system's behavior. Most importantly, the system delivers highly accurate air quality index predictions through a API, making it easy to integrate into other platforms such as Make My Trip or health and travel applications. Dataset overview. In our project, we used a dataset containing 12 critical air quality features, namely PM 2.5, PM 10, NO2, and many more gases which are present in the air. These features were carefully selected based on two key factors: their significant environmental impact, their strong correlation with the air quality index. This selection ensured that our model focuses on most influential pollutants affecting air quality. This is the dataset which we use to train the model for the predictive analysis of air quality index. The dataset was collected from Kaggle. Around 30,000 different combinations of gases values were used to train the model.
Now we are going to see how the data preprocessing has been done. Handling missing values. We started by filling in or removing any missing data to make sure our model gives accurate and reliable predictions. Normalizing numerical features. All numerical values were scaled to a common range so that each feature has equal importance during training. Encoding categorical variables. If there were any categories like names or labels, we converted them into numbers so the machine learning models could understand them. Time series formatting for LSTM. For the LSTM model, we organize the data into sequences, which helps the model learn patterns over time. Feature selection. We choose the most important features that affect air quality the most, which helps improve model performance and reduces the chance of overfitting. Predictive modeling with machine learning algorithms. The two machine learning algorithms used in this project are random forest and gradient boosting model. The random forest regressor is used as one of the base models in our ensemble system. It is trained separately using pollutant features to predict the air quality index. It works very well with high dimensional data like pollutant concentrations, example PM 2.5, NO2, CO, and many more. Since it builds multiple decision trees and averages the results, it is robust to noise and outliers in the data. The model reduces the risk of overfitting by relying on an ensemble rather than a single tree. It can effectively capture complex, nonlinear relationships between pollutants and air quality index. Random forest is not sensitive to the scale of input features, making it ideal for real world data with varying units. Overall, it is excellent for understanding how different combinations of pollutants affect air quality. Coming to the gradient boosting model, gradient boosting is used in two ways. First, as a base model trained directly on air quality index features, and second, as the meta model in the stacking ensemble. As a meta model, it takes predictions from random forest, gradient boosting, and LSTM and combines them to give a final output. It builds decision trees one after another, with each new tree correcting the mistakes of the previous ones. It offers fine control over learning using hyperparameters like learning rate and tree depth. It is well suited for capturing complex patterns like subtle relationships between pollutants. Helps reduce bias, which complements random forest sense in reducing variance. As a meta model, it effectively balances random forest's ability to handle static patterns and LSTM's strength in capturing time based trends. Deep learning for enhanced air quality forecasting. The deep learning model used in this project is long short term memory or LSTM. LSTM is a deep learning model trained on past air quality index data. It learns patterns from previous time steps to predict future air quality index values. The predictions from LSTM are used as input for the final gradient boosting model. LSTM is designed for time series data, which makes it ideal for AQI that changes over time. It uses memory cells to remember important patterns from the past. This helps it capture trends, seasonal changes, and sudden increases in the pollution. Unlike tree-based models that look at data points one at a time, LSTM understands how values change over time. This adds a time-based learning layer to the system, improving overall prediction accuracy. Now let us see how the ensemble approach works and why we should use all the three algorithms. Random forest contributes strong base level predictions using decision tree based ensemble learning, excelling at capturing static tabular relationships. Gradient boosting base level offers another perspective by focusing on correcting residual errors from previous models, enhancing predictive precision for static features. LSTM introduces deep temporal insights by modeling sequential dependencies and trends over time, addressing the limitations of static models. The ensemble meta model, or the second gradient boosting model, serves as a meta-learner that combines the outputs of random forest, base level gradient boosting, and the LSTM. This meta-learner intelligently learns how to integrate the strengths of the three diverse models to achieve more accurate and robust air quality index predictions. Now we will see how the model training process works. During training, we ran each model individually and monitored their performance. The deep learning model was trained over several epochs using metrics like loss and accuracy to fine tune the results.
Now we will see about the code which is used for predicting air quality index. We start by importing Pandas, a powerful Python library used to handle and manipulate data in tabular form like Excel spreadsheets. Next, we import NumPy, a library used for numerical operations like arrays and mathematical functions. This helps us split our data into training and testing parts so we can evaluate how well our model performs on unseen data. We use standard scaler to normalize our feature values, making all features have a similar range, which helps model learn better. These are two different machine learning models, random forest and gradient boosting, both of which are great for prediction tasks. We import metrics to evaluate how good our model predictions are. R-squared tells us how well the model fits the data, and RMSE shows error size. Here, we import tools to build a neural network using Keras, particularly the LSTM model, which is good for handling type series data. These libraries helps us create a simple graphical user interface so users can interact with the model without writing code. We load our dataset from a CSV file and fill in any missing values using forward fill, which copies the last valued value forward. This function creates new features from data to help the model learn better. It takes in the data and a target column like air quality index. We add lag features, meaning values from the past. For example, air quality index from 1 hour ago, 2 hours ago, etc. We also add rolling statistics, average and standard deviation to show recent trends in air quality index over time. After adding new columns, some rows may become empty, so we remove them. We apply our feature adding function to the dataset using different time lags. We separate our features from the label, which is the air quality index we want to predict. We scale the features so each one has a similar range, which improves training performance for many models. Now we split our data set into training and testing parts. We define a function to build our LSTM model. LSTM stands for long short-term memory, a type of neural network that remembers patterns over time. We create a deep LSTM model with two layers. Dropout else prevent overfitting, and the dense layer gives us the final prediction. We compile the model using the Adam optimizer and mean squared error as the loss function. We reshape our data to fit what the LSTM model expects, a 3D shape, example samples, time steps, features. We train the LSTM model using our training data over 10 iterations or epochs with 32 samples per batch. We train a random forest model which uses many decision trees to make a strong prediction. We also train a gradient boosting model which helps build trees one after another to reduce error. We make predictions from each model: random forest, gradient boosting, and LSTM. We stack predictions together and train the final model, a meta model to combine them into better overall prediction. We use the meta model to generate final predictions. We evaluate how accurate our final ensemble model is using R square and RMSE. We define a mock model to simulate predictions for the graphical user interface. You can replace this with your actual trained model. This function reads values entered in the graphical user interface, sends them to the model, and shows the result. This function lets users upload a CSV file to load a new dataset into the graphical user interface. This code builds and runs the graphical user interface window, adding labels, input boxes, and buttons, and also result text. And after all of this, finally we plot the actual versus predicted air quality index values to visually compare how well the model performed.
Now we are going to see the working of the model or the demonstration of how the model works. Welcome to the demonstration of our project AI-driven air quality forecasting. Our goal is to accurately predict air quality levels using a combination of advanced machine learning and deep learning techniques, achieving an exceptional R-squared score of over 0.99. This project features an interactive graphical user interface built with tkinter designed to provide a seamless experience for data analysis, pre-processing, and model training. What you're seeing here is the model training process where the deep learning model is being trained over multiple epochs. The training is based on a dataset containing 12 carefully selected features which play a significant role in determining air quality. The live feedback from the training include metrics like loss and accuracy for each epoch, ensures transparency and helps fine-tune the model. Our deep learning model is the core of this project. Built on a robust architecture, it ensembles two machine learning and a deep learning algorithm, which captures complex patterns and relationships in the data. What sets this project apart is its future scalability. We aim to develop the system as an API key that can be integrated into platforms used by the industries, governments, and organizations for real-time air quality monitoring. Companies like Google, IBM, Honeywell, and Philips, as well as environmental agencies, could benefit from this solution to enhance their applications in smart cities, healthcare, and pollution control system. In conclusion, AI driven air quality forecasting is more than a prediction tool. It's an innovative solution leveraging machine learning and deep learning to transform air quality monitoring. With its potential to integrate into various industries and applications, this project promises to pave the way for a cleaner and healthier future. As you can see on the screen, the output demonstrates an AQI prediction API delivering highly accurate results by leveraging an ensemble model that combines random forest, gradient boosting, and LSTM predictions. The system has achieved an impressive 99% accuracy. This high precision is reflected in the evaluation matrix and the visualization where the predicted AQI values closely align with the actual AQI levels for the first 100 samples. This demonstrates the API's exceptional capability to provide reliable and real-time AQI forecasting, making it a powerful tool for environmental monitoring and decision making. Let's take an example of where the air quality index prediction could be integrated so that it helps in our real life. Let's talk about a practical example. Our API can be integrated into travel booking websites like Make My Trip. Imagine a traveler is planning a vacation to a city. When they search for tickets, the system can display the predicted air quality index for the travel dates. This allows the user to decide whether it's a good time to visit or not, especially if they have respiratory issues or they are traveling with their children. Coming to the future scope, let us look at the future scope of the air quality index prediction. In the future versions, we plan to use larger and more diverse datasets. Deploy the API in cloud for real-time service. Integrate it with the mobile apps. And use deep learning models like CNN, LSTM hybrids. Coming to the challenges, some of the challenges we faced includes cleaning and pre-processing inconsistent data, avoiding overfitting in LSTM, balancing speed and accuracy in ensemble models, API deployment for real-time processing. At last, we can conclude to sum up, our AI driven air quality forecasting system is not just a model but a real world tool ready for integration. With its high accuracy and scalable design, it can support informed decision making and potentially save lives. It represents a significant step towards cleaner and smarter cities. Thank you.